Geez, I gotta remember. Okay. We're bored of p orbitals and s orbitals. Let's hit d orbitals. If you can do this and you can construct a band structure based upon d orbitals, I can pretty much give you any system and you could develop a band structure for a 1D system. We're going to have an eclipse stack of square planar platinum complexes with 4 ligands. You guys might have talked about this compound in the past. Does anybody know what it's called? Cisplatin. It's a therapeutic for cancer. It's one of the best chemo agents we have. It's pretty amazing in terms of the production of it. Most of the platinum comes from Africa. And the crazy part is Africa has the least amount of this, which is strange. The reaction to make it is a very beautiful reaction. It's a very strong chemo drug, and oftentimes it's mixed with other drugs. Is it expensive to make or no? Yes, because it has a very short lifetime. So you probably wouldn't. No, you could. Actually, it was made by accident. And Dr. Gaboo, who is here, was in the lab next door to the lab that first synthesized this thing. And what they noticed is they never had to change their water bath. Never needed to put any antimicrobial stuff in it. It always stayed clean, and people were curious on how that was. And it led them down the rabbit hole to figure out, hey, they were polluting their water with this stuff, which was keeping it clean. Yep. They mix it with other stuff, but this is still one of the most effective ones. That's an example of a square planar complex. So when I say square planar, how many dimensions am I really talking about in that case? 2. So what we're going to do, another one, is we're going to consider a system. We have a chain of a D3 platinum ligand complex. Okay, you might not know what I mean by D3, but what I mean is after the ligand has interacted with the metal, there are 8 D electrons. You talk a lot about it in inorganic chem. This system. D3 or D? Oh, I'm sorry, D8. I said D3. Sorry, I played D3.5 edition for Dungeons and Dragons, and I just get stuck there. People hate it because they call it Homework the Game, and I like it because it's like Homework the Game. Yeah, Pathfinder sucks. Thank you. This is the system we're going to consider. We're going to neglect talking about the potassiums, but you can import this structure into Avogadro, and what you will see is a chain. It's pretty neat to look at. And this shows a stacking with, if we're considering the distance between platinum and platinum distances, it's approximately 3.3 angstroms. That's based upon Rold's discussion or Dr. Hoffman's discussion in his review. I haven't looked at the most current data, but I gotta believe X-ray refinement shows a more accurate number at this point. So what we're going to do is we're going to have each of our platinum centers stationed this way. And they're square planar complexes. So there's each of our platinums. Since we have 4 cyanide ligands, we're going to put, each one has 2 in the plane of the board. One cyanide's coming out of the board. And if I have them positioned that way, where's the last one? Yep, in the plane of the board. So what's the distance between these two? Or what's our unit cell length? Yep, it will be A, 3.3 angstroms. Now, we're going to specify our directions. These are a little bit different. We're going to have X going down, Z going this way. Okay, everybody feel comfortable or feel like they understand what we're doing here? Okay. These are eclipsed. They are not staggered. Staggered will change the structure more so. Eclipsed, is this favorable to have it be eclipsed? Most likely not, but we're going to keep it that way. Yeah, Joe? In some cases, yes. In other cases, no. I actually don't know which one is the ground state minima, but I would guess that the staggered would be more favorable. I don't know if that's true, though. There are systems where it's not. For example, if you consider fluorinated compounds and you look at does staggered or eclipsed win out, in some cases, eclipsed is more energetically favorable compared to a staggered. Yep, there's situations where it can form intra-hydrogen bonds, or you have something called hyperpolarizability or hyperconjugation. They use a bunch of magical words to say it's the energetic. But everybody feels comfortable with this now, right? Okay. So the first thing we're going to ask, which is important for us, is if we're considering the molecular system, it's very important to be able to start at the molecular and extend it to the periodic. What does the crystal field / MO diagram look like for this complex? Has anyone talked about crystal field or ligand field theory? You definitely, I would assume you would have.
We definitely did, but I could not tell you at this very second.
Okay. It's basically a dumbed down version of MO theory, where you have everything act like point charges and you see what happens to the d orbitals, because the d orbitals will split as you have ligands approach it. Ligand field theory and crystal field theory were developed by physicists first and extended to molecular systems. That was impressive. Okay, so we're going to draw a diagram that is representative of what you'd get out of MO theory. MO theory would be more complete. There's just more lines and it's messy. But what you would find is a splitting that looks like this. Okay, so now let's think about the platinum. Ligand, 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 ligand. And there's going to be some splitting that occurs because we're pushing negative charges closer to this system. What we would find is the following splitting with each of the d orbitals. Yep. Where this is that plane. Okay, what type of complex did we say this platinum system was? A D what? D8. Okay, a D8. So that means we have 8 electrons to fill. Let's start filling our electrons. 1, 2, 3, 4, 6, 7, 8. And that's what the molecular system looks like. But in this class, we don't talk about molecular systems a ton. What are we going to jump to? Periodic systems, infinite chains. Call me Scott Two Chain Simpson.
Yeah, I looked up, I was trying to find another YouTuber also named Scott, and the person that popped up on my Scott was Scott Simpson. He is Scott Simpson.
Really?
Yeah,
I'm famous.
Every time you post a YouTube video, it's always another guy.
Ha! I'm famous, son. I'm an influencer now. I can quit my professor job and live off of stupid merchandise. What are those Funko Pop things?
I think I'd actually, would you guys buy a Dr. Simpson?
Funko Pops are a sin against God.
Yeah, I agree.
I would buy like a Funko Pop. But it actually needs to be the outfit you're wearing now. It's more different. The flannel and like the
Yeah.
great shoes.
Yeah, do you want off the grid Dr. Simpson, or do you want like the... Okay, so what we're going, despite that, we're going to look at the block functions at the zone center. What is the value of K at the zone center? Yep, and at the zone edge, what's that? Pi over A. In this case, our A is 3.3 angstroms, but we can just leave it as A. We have to consider all the different d orbitals. So we got the dz squared. What other d orbitals do we got? Yep. 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 There we go. And we should all know what those functions look like from the solutions of the Schrodinger equation applied to the hydrogen orbitals or from Gen Chem. Okay, so what we're going to do now, you'll want to give yourself about half of a page. We're going to make a table. Can I erase this bit that I just wrote? Or do you guys need time? Good. Am I cool, Katie, to erase it? Okay, we're going to make a table. We're going to have the orbital. We're going to have what the block function looks like at the zone center and what the block function looks like at the zone edge. Let's consider the dz orbital first. Okay, now these are the centers of our platinum. And remember, we said the z direction is propagating this way. So if I draw my first orbital, what does the dz squared look like again? Yep. Yep. And then a ring. Okay, the wave function changes sign somewhere. Where does the wave function change sign between? Yep, the donut and the center, right? So let's color in that donut. But the lobes have the same sign, right? Okay. Now we're at K is equal to 0. There is no phase change. So what should I draw for the next one? Yep, the exact same, shaded the same way. And then the last one, same thing, still correct? Okay, great. Let's look at this. What type of overlap is this? Okay. Is it constructive or destructive overlap? Constructive. So this is a bonding, sigma type bonding orbital. crystal orbital. Yeah.
Is there also the delta bonding?
We'll talk about that one in a minute, but yeah. Okay, now pi over a. What happens between the basis functions at this point? Switches sign. So I'm going to draw it this way, but how should I fill this thing in? Yep, so the lobes get shaded in, like the P lobes. And then what about this last guy? Yep. Okay. Now, what type of overlap is this? Yep, it's a sigma star because we have destructive interference. Okay, what orbital do you want to tackle next?
DXC.
Okay, let's do DXC. Okay, remember, Z was propagating that way, X was propagating that way. Is that because that's how you drew it in your notes, Devin?
Correct, I don't have to erase it.
Ooh.
Okay, let's draw this one out. How does this orbital look? The DZ squared is the kind of weird one.
What's the
Yeah, 4-leaf clover. Okay, there we go. There's one of them. How do we need to shade this thing in? Yeah, sure. I like this way. Now, at pi is equal, or excuse me, at k is equal to 0, is there a phase change between the basis functions? Right, because the sign doesn't change. So I'm going to draw these. How should I shade this one in? Yep. Next one, same thing still, right? Okay. How many regions of overlap between the two basis functions? So what type of overlap is that? Okay. It is a pi star because what type of interference do we have? Yep, deconstructive. So that's a pi star. Does everybody feel comfortable with that one?
Oh, this is why we don't use
That's why I don't like to say in phase and out of phase, because when we're talking about phases, we're really talking about the formation of the block functions and the sign change between the basis functions. So most chemists who are molecular, in phase, out of phase usually doesn't matter too much, but when you move to solid state, that's where it starts to become more of an impact of what you say. Okay, this one, I'm going to shade it this way. Okay, how should I shade the next AO? Yep. The next one? Yep, because we're switching sign completely. What type of overlap is this? It's constructive, and how many regions of overlap? Yep, so constructive, bonding, pi. Everybody feel good with that one? Okay, what orbital do you want to do next? DYZ. Perfect. Why'd you pick that one, Joe?
because we talked about Z, so let's do all the Z's.
Oh, we could do it, yeah.
Yeah.
Now, YZ, look at the molecular picture. It's degenerate. What would be the only difference? Yeah. Yep, it would be coming out at us. That's hard to draw. So what I'm going to say is and DYZ. Perfect. Almost like it was planned.
2 steps.
Yeah. Perfect. Okay, which one do you want to do next? We already did XZ.
XY is what I meant.
Okay. DXY. This one's going to suck to draw, but we're going to do it. I feel like I've used that phrase
A lot, yeah.
this last weekend. My daughter has to get monthly injections of this stuff called Dupixent for her allergies, and I tell her she's going to have a shot, and she's like, and I'm like, it's going to suck, but we just got to do it. She's, okay. Not as bad as a shot, but pretty close. How am I going to draw the first atomic orbital here?
Is there gonna be like a cross now?
Yeah. So we're going to try to draw it in the plane, sort of like that, where I'm trying to show,
You're drawing it like this.
yeah, that it's slightly tilted, but you can like look at it from a perspective. Okay, how do you want to shade this one in? Okay. Okay, K is equal to 0. Block functions, basis functions do not have a phase or sign change. So how should I should fill all these in how? Yep, the same way. What type of overlap is this? How many regions? 4? Yep, it's a delta. And constructive or destructive? Constructive, so that's a delta. Now, if I fill in this first one here at K is equal to pi over A, what should I do with the next one? Yep. Then we return back here. So what type of overlap is all of this? Yep. Deconstructive, it's a delta star. Okay, the last thing I would like to do is plot this. Am I okay to erase this bit? Oh, yeah. What's that one going to look like? It's almost the same thing as this guy, but it's been rotated by, what, 45 degrees?
Yes.
Yep.
So you're just rotating around, so you like
Yeah.
sticking out a fork or all.
And it would be aligned right with your axes. So they're the same functions. Now, are they degenerate technically based upon our crystal field diagram? No. Okay. So now what we're going to do is, am I okay to erase this? Because you guys have this information?
Is that because they overlap the ligands, the X squared and S squared?
Yes. Yep. And also, if you look at it from an MO picture, sometimes there's other stuff going on there too. Crystal field explanation, yes. Am I cool to erase this now?
You mean the rotation of the... So rather than being like an X like this, output, so just rotate to it once.
Okay.
It can rotate out.
So it's kind of like I thought it was
Yeah, exactly. So as you were thinking of the X, well, this is the X squared minus Y squared, you were thinking, but this is the one that we did.
We can quickly sketch out the band structure for this thing. Okay, looking at this, we want to have the center of the bands kind of match this orbital energy. Okay, so, but they're going to have different amounts of dispersion. Which one is going to have the greatest amount of dispersion out of all of these? So look back at your block functions. Yep, the d is z squared. So the d is z squared, we're going to show it going like that. Okay, what about, what's going to have the next largest amount of dispersion? Yep, dxz and dyz. What type of overlap do they have again? Pi. So what does that mean about the band dispersion compared to the dz squared? It's less. But now that the middle point should be a bit lower than the midpoint of the dz to match that, we're going to show it like this. So there's my dxz, dyz.
Why wouldn't the bottom of the band at pi over a equal of dz squared if in the end all picture is lower in energy?
Just because the dispersion associated with it is larger, the other aspect to it is the bonding combination is more favorable in comparison to the bonding combination on this side. That's an unfilling answer. And also the d orbitals just have better overlap that way. Okay, what else are we missing? Mm-hmm. Yep. And the way, that one's, which way is it going to run? Yep. And it's delta overlap. Delta overlap is really, really crummy. You essentially get a straight line there. And then way up here is our dx squared minus y squared. Okay. Next time we'll fill in some electrons. We'll start looking at, we'll use a term called the Brillouin zone, and we'll start talking about densities of states. For now, does this